Hi, everyone, and welcome back to the Regression and Beyond series. In this video, I'm going to be expanding on what I covered in the last couple videos on generalized linear models. Now we're going to be focusing on some specific generalized linear models that you might use if you have a count-dependent variable. Now, per usual, the script file I'm going to be running through as well as the data are linked below. So let's get right into it. Starting out, we do kind of the typical thing that we almost always do, which is importing the data and then having a quick look. In this case, we have three independent variables, x1, x2, and x3. And then we have, and those are all continuous variables, and then our dependent variable, y, which is a count variable. So a typical starting and potentially it can be the ending point as well with a count variable is to use a Poisson model. So when we go to run this and you look at the command, you'll see it's pretty similar to the other GLMs that we did before, except we have a slight difference here. We say the family is Poisson, and then the link is log, so the log link. So previously, we had done the logit link, often with like logistic regression, but here we're doing a slight difference. So a slightly different distribution and a slightly different linking function, but otherwise it's pretty similar. So let's run that and have a look. Again, we see kind of the typical output that we're used to with the other GLM, so coefficient, standard errors, p-values, and all that. So we can do virtually everything that we did previously with the other GLMs could also be done here. I'm not going to run through all of that, but one of them is exponentiate. So when we did a binomial model and used the logit link and then exponentiate the coefficients, we got what are called odds ratios. So similarly here, we're going to exponentiate, but they're going to be called something different. Often they're called risk ratios or incident rate ratio, but they're interpreted roughly the same way. So an example I have in here would be the idea of a 1 unit increase in an independent variable results in some percentage increase in the log count or incident rate of y. And you can convert them into percentages similar to how you would do that with an odds ratio. So to exponentiate, I'm just going to use this command right here to do that with the coefficients, and that's how you would do it. Another thing we did previously was test our kind of hypothesized model, we could call it, versus an intercept or null model. We can also do that same thing here. So let's go with that. We're going to do an intercept only model. So everything is the same, except now it's just an intercept only model that we're going to run. And not important to look at it. Just want to illustrate, again, just intercept only. And then we can do a likelihood ratio test because these are what we call nested models. So 3 degrees of freedom difference here. That's because we have the 3 independent variables versus when we had the intercept only. You get the chi-square, and then you get the p-value. And remember, with this test, the null hypothesis is that the models are equivalent. They provide an equivalent fit to the data. So in this case, the p-value right here would suggest that they are not equivalent. Our model with the 3 independent variables is better, simply put, than the intercept only model. One brief note on this is you actually don't need to go through the steps of estimating that intercept only model and then testing it. I kind of like to do that just so you can remember all the steps and have control over things. If you just do the LR test command here with just that model, it'll automatically do it. it just rotates the order, resulting in the negative degrees of freedom. Not actually negative degrees of freedom here, so that can be a little tricky, but if you get rid of that, everything else is the same. So that can be a kind of a quicker route to do it. You just have to remember to ignore that negative part. Now, although we're moving away from traditional linear regression, where we often make this assumption that the residuals are normally distributed, for example, now with GLMs, we are assuming a different distribution, but that doesn't mean that we no longer have assumptions. They can just be different ones. So in this case of Poisson, an assumption is that the conditional mean is equal to the conditional variance. So we can look at that here, specifically the mean of the fitted values from that model and the variance of the residuals. So relatively close, but not exactly the same. So just looking at that would suggest that we have violated that assumption. Now, formally, the fitted values and residuals are what you want to look at, but you can basically get the same idea if you just look at the mean and variance of the dependent variable. Technically, we're not making any assumptions about the univariate distribution of the dependent variable here. So we want to look at those fitted values and the residuals, but just want to illustrate it basically gets at the same idea as these things are related. Now, similar to kind of before, when you have a violated assumption, and in this case, this specific violated assumption, it can result in biased standard errors in terms that you get wrong p-values, and maybe you can reach the wrong conclusion. So what you could potentially do at this point would be to estimate robust standard errors. I have a video talking about that, and you would apply that here if you wanted to. Alternatively, you can add an additional parameter. Specifically in this case, where the variance is greater than the mean, we call this overdispersion. So what we can do, or one way of kind of trying to account for this, is basically to add a parameter that accounts or kind of represents that overdispersion in our model. Now, this is going to lead to what we call the negative binomial model. And quickly before I get to that, I wanted to note this. There are other types of things you can run into, like under dispersion rather than over dispersion. I'm not going to talk about under dispersion, but note that is a thing. And there's also routes you can take to model or address that. But here, talking about over dispersion, relatively common situation to run into, at least in my experience. So now we're going to move to this negative binomial model, which is really just an extension of a Poisson model. Now we're adding this over dispersion parameter. We're going to load the math package to be able to do this. I'm going to run it, and you see the command for the formula is very simple here. We don't have to specify a lot of things. And now let's look at the output. So on the front end, things are looking pretty similar, right? But kind of one of these more unique things that pops up is we see this theta right there. Well, in this mass package in R, theta captures that dispersion parameter. Specifically, theta is 1 over the dispersion parameter. Brief thing to keep in mind with this is in other software, it's common where they'll just report the dispersion parameter. So if you are communicating results with people who might be using different software, you might want to just specify whether you're reporting theta or the dispersion parameter. And notably, it's easy to get to that dispersion parameter. So we can just do 1 over theta and then actually get to the dispersion parameter if you did want to report that, maybe instead of theta. Again, you can exponentiate and do some of the other things that we've done with GLMs. I'm not going to do all of that for now, and we're going to kind of move forward. Now, a basic next step that we'd want to do is now test our negative binomial model against that Poisson model. Basically, we added this dispersion parameter, right? And we want to see, okay, does that make the model a better fit relative to the other one we did, that Poisson model? So we can do this likelihood ratio test, get 1 degree of freedom here, again, because it's just with and without the dispersion parameter, chi-square, and the p-value. So in this case, it is statistically significant, and this would provide a pretty good justification for going with a negative binomial model. Some other software, and depending on your approach, an alternative one to doing that rather than testing the nested models, Poisson versus negative binomial, you just estimate the negative binomial, and then you can actually do a test specifically. So in this case, again, we're using theta, so we can basically test the null hypothesis that theta is equal to 1. So here I just took theta divided by the standard error, turning it into, potentially you treat it as a z or a t. I'm going to treat it as a z in this case, and we can compare it to a critical z-score. And then this one's bigger. So basically we'd reach the same conclusion. Again, that it's meaningful more or less to add to this, add that dispersion parameter and use the negative binomial model. Now, in many cases, again, I mentioned with Poisson, it can be often a starting and ending point. And even if you go beyond it, then often the negative binomial model will kind of be your ending point. But depending on the particular kind of situation you're in and what you're kind of doing this analysis on, another thing you might want to consider as well with count data is the zeros, and specifically kind of too many zeros. And we'll talk a little bit about what that means, too many zeros. And this is going to lead us to all this language of zeros, the zero-inflated models. So here I just looked at the number of cases that take on a value of 0, and then I turned it into a percent, so we can have a kind of clear understanding. So we see here that over 40% of the values are 0. Now, how much is too much? Not really a perfect answer. One simple thing you can rely on is kind of common sense, right? Over 40%, that is a lot of zeros. So just intuitively, that might seem like too many. Now, it can be a little bit complicated in particular circumstances, but here just to show you, it actually is possible to basically estimate the expected number of zeros that you would get. So that's what I'm going to run through and kind of show quickly here. So like with a Poisson model, how many zeros would we actually expect? And in our particular case, about 163, but we already know that our dependent variable has 211. So generally the common approach to addressing this too many zeros aspect of count data is to do a zero-inflated model. And basically you can just do a version that's a counterpart to Poisson and negative binomial. So you can do zero-inflated Poisson and zero-inflated negative binomial, or that's what we're going to do here. So you may need to install this new package to do it that we're going to use. Then let's start with a zero-inflated Poisson. See the command just to illustrate, relatively similar to what we've done before, specifying a distribution and the link. Something that might pop out is now we're specifying the link as logit. We're going to talk about why that is. But looking at the output, you can probably figure it out yourself to some extent. Really, we estimated this model, but if you look at it, it looks like 2 models. And that's basically what we're doing. Technically, it's 1 model with 2 components, but it's easy to think about it as we're basically estimating 2 models. On the top here, And this is going to be focusing on specifically the count. That's the Poisson with the log link. So what we kind of just did a second ago. This bottom here, you see the binomial with the logit link. So this is what we did in the previous lab when we had like a binary dichotomous dependent variable and you did like a logistic regression model. So that's actually what this is right down here. So a few points to kind of make about this. Overall, this is the type of what's called a mixture model, which aims to generally kind of capture and model these latent subpopulations in your data. So in this case, what we're actually trying to capture, and I'm going to use the example that I've had experience running these models with things like criminal victimization, especially certain types of criminal victimization, where basically we kind of have two groups of people, where one group is we could almost consider, and the language is often used as immune, as people that basically have no risk of being victimized in a particular way, to use that as an example. And then we have this separate group that, whether or not they actually were victimized by a particular crime during this particular study period, they did exhibit or they were at risk of being victimized. So that's the idea of we're trying to capture, again, these kind of sub populations here. And one thing that can be a little bit tricky in terms of how you interpret. Previously, when we did the logistic regression, you have a binary like a 0 and 1 that you're predicting. Typically, we're interpreting and focusing on how things relate to the probability of taking a value of 1. Where in this case, we're kind of flipping that on its head. And this is actually, the results here are going to be relating to the odds that the value is 0. So make sure you keep that in mind, because that can be a little tricky. And that's why you're also, it's not uncommon to see like rotating signs potentially among your independent variables, right? Something might increase immunity or make someone basically have no risk, right? Be immune, but then have common a potentially opposite effect on something like the risk of victimization. Now, with these models, I just use the same 3 independent variables. And I already mentioned that you might see just one variable have a relationship to the count part, and then kind of a different or maybe counterintuitive initially when you're looking at it, relationship to the probability of being 0. Well, you can also specify independent variables that maybe only relate to one thing. So using that kind of crime victimization example, you might include one set of factors or whatever that focuses on, these relate to risk of being victimized by a particular type of crime. And this other one is related to immunity, or these other variables are related to immunity. But it definitely can be quite tricky. So you just want to make sure you can have some strong justification for whatever you decide to do. Again, as I've noted, we could exponentiate. Again, here, again, with the binomial part, those would be the odds ratios. And then the Poisson part, we'd interpret like we did before, like an incident type interpretation rather than an odds ratio type interpretation. But I'm not going to do all that at this point, but just want to note that you could. The next thing I want to do, just as we went from Poisson, then added that dispersion parameter and did the negative binomial, we can also do that with a zero-inflated approach. So that's what we can do next, what I just ran here. You'll note the only difference is that distribution specified as negative binomial rather than Poisson. And then if we look at it, again, it basically looks the same, except now we have the negative binomial with log link. And otherwise, this part right here is the same. So at this point, we have estimated 4 models in total. Now, when models are nested, and in this case, like generalized linear models that are nested, you can do a likelihood ratio test. But when they're not nested, you have to use potentially some other type of test. So I'm going to introduce and show this one specific test, the Blanc test, though I'll briefly note that there are some important criticisms and limitations. So I'm just going to show it, but probably don't have this an end all be all for the decisions you are making. Like the other likelihood ratio test that we've been doing, it's a similar idea of the null hypothesis being that these models are statistically the same. Basically, they provide the same fit. So we would have to use this if we wanted to test something like the Poisson versus the zero-inflated Poisson. They're not nested, so we'd have to use something like this. Or not that you'd have to, but you might use something like this. Interpretation, basically the same, right? So if it's a really tiny p-value, typically, we'd say it's significant, so the models are significantly different. So in this case, the zero-inflated Poisson is a better model than the regular Poisson we did. We could now do the same thing with the negative binomial. So the regular negative binomial versus the zero-inflated version. And we get a similar idea here. Okay, zero-inflated version is better. And then finally, to compare the two zero-inflated models, we can use the likelihood ratio test because these models are nested. In this case, basically no difference. So what would you do in a situation like this? Well, it could depend on, of course, several factors. But in this case, probably the best model to go with might be that zero-inflated Poisson model. Now, you might be thinking, oh, well, didn't we have that over-dispersion situation? And we did. But it's possible that over-dispersion can be the result of zero inflation. Just an important point to keep in mind with that one, however, is that a zero-inflated model isn't necessarily going to address over-dispersion. They are distinct issues, even though, again, like too many zeros or something like that can be, or I'm sorry, over-dispersion can be the result of too many zeros or that zero inflation. To kind of return to this idea, like I think it would probably be the zero-inflated Poisson, probably be the model that I would go with here. But with these approaches, I think it's, on one hand, it's exciting because there's lots of different directions you could go, but there always isn't going to be kind of a really clear, like, you should do this at this particular time. So it's always a good idea to have really strong rationale behind your modeling. And as I mentioned, with something like the non-nested model test, you really don't want to plan on like relying on something like that exclusively. You're going to want to have some other arguments and thoughts with your approach. So you can look through all these models and maybe come up with your own context and think about what would be the most kind of appropriate model that you'd want to present. Well, I hope this video was helpful. Thank you for watching, and I look forward to seeing you in future videos. See ya.